All right, well, one of these days, I'm gonna figure out how to do my job. Okay, I'm sharing, I'm recording. It's done. I swear I'm good at this. Anyway, what were we doing? That's right, we're trying to finish 5.3 notes, and we are going to start by proving this tangent reduction formula. And I was trying to say something intelligent about this formula before we realized I wasn't sharing my screen. But anyway, this plus or minus on the left, I need you to see that it's a plus or minus on the right side on the top, but on the bottom, it's a minus plus. What that means is on the right side, it's going to have the same symbol that you had here on the top, but on the bottom, it's going to have the opposite symbol. That's what that's telling you. Why is that happening? What's happening because tangent, if you remember, is sine over cosine. So on the top, it behaves like the sine sum or difference formula, which has a matching symbol. But on the bottom, it behaves like cosine, so it uses the opposite symbol like cosine does. So that's why that's happening. Cool? All right. So of course I'll write the formula on here because I don't have it memorized. I'm just going to pin it up here. So we have tangent of a plus or minus b equals tan a plus or minus tan b. This is obviously where a and b are angles over 1 minus plus tan a tan b. All right, that's what it says on the front. There's our formula. So let's make this happen. Angle A is going to be theta. Angle B is going to be 3 pi over 2. And we have a minus. So what we're going to say is that tangent of theta minus 3 pi over 2 is, I'm going to have a matching symbol on top. So tangent theta minus tangent 3 pi over 2 divided by 1 on the bottom. I'm going to have a differing symbol, so I'm going to have a plus down here. Tangent theta times tangent 3 pi over 2. So we just need to evaluate tangent of 3 pi over 2 and pretty much set, right? Let's see, 3 pi over 2 on my quadrantals is 3 pi over 2 is below though. So 3 pi over 2 is down here. The the coordinates at this point are 0, comma, -1. And I don't really need the radius. I mean, the radius is 1 because it's talking unit circle. But the reason why I don't need it is because tangent is the y value over the x value. So what is tangent at 3 pi over 2?
0.
It's y over x. It's undefined. Yeah, it's undefined. You can't divide by 0. What? Undefined? Okay, well that doesn't make any sense because we were told to prove that it equals negative cotangent theta. So something must be wrong here. It's not that the identity is bad, this formula that we've written. That's not it. It's that it doesn't always work. There are times when tangent is undefined. And if tangent happens to be undefined in a place, you would kind of want to steer clear of the formula that's full of tangents. So what would you do? Well, what you would do is you would remember that tangent of theta is, there you go. Since it's sine over cosine, we're going to use the sine sum or difference equation over the cosine sum or difference equation. So I'll switch colors, move over to purple. Purple feels good. So the top will be sine of theta minus 3 pi over 2, which will use the sum or difference identity there, and the bottom will be cosine of the exact same setup. So we'll use the cosine sum or difference identity on the bottom. There. Now, the reason why we would want to do this is because we're hoping that this thing down here will not equal 0. Of course, it had better not, because we know we have to get the negative cotangent theta, so we better not get undefined again. The sine identity goes sine cos, cos sine, same symbol. Sine cos, cos sine, same symbol. So if there's a minus here, there's a minus here. The cosine identity goes cos, cos, sine, sine, opposite symbol. Okay, well, hey, now the radius matters to me because both cosine and sine are going to use that radius of 1. So we can reference this because we're still talking about 3 pi over 2. So we're just going to reference this right here for our x, our y, and our r. You can't cancel because there's pluses and minuses in your way. The only time you can cancel things off the top and bottom is when things are separated by multiplication dots. No, but these terms are separated by addition and subtraction. When your terms are separated by addition and subtraction, you cannot cancel things off the top and bottom. Alrighty, what do we got? Let's see. Equals sine theta. That's not going to matter. Now, cosine of 3 pi over 2. Cosine is x over r. X over r. That's just 0. Minus cosine theta. Sine of 3 pi over 2. Well, sine is y over r. So that's negative 1. All right, so the top is just going to be positive cosine theta because 0 times sine theta is nothing. On the bottom, we do have a cosine theta. And we just said that cosine 3 pi over 2, look, it's the same here and here, was 0 because it's x over r. So yeah, 0 plus sine theta, and the bottom sine 3 pi over 2 is the same as the top sine 3 pi over 2. Again, y over r, so negative 1. Again, this is going to give us a 0. We don't need to worry about it. The top becomes positive cosine theta. The bottom is negative sine theta. And that is negative cotangent theta. The top is positive because this negative and this negative cancel each other. So yeah, I'm gonna be honest with you. There are times when using the sum or difference identity for tangent is faster than using sine over cosine. But because I've run into undefineds several times in my practice, I have just immediately moved over to sine over cosine sum of difference identities. I honestly rarely use this formula because I'm afraid that I'm going to have wasted my time and get an undefined that is a lie. So again, this thing works as long as your sine, let's see, as long as the bottom is not undefined if you were to have looked at it like this. And I'm trying to think of a time when this would be undefined. This would never be undefined because it's impossible for this and this to be the same thing, one positive, one negative. I think. Now that I've said that, I'm scared. Okay, what I just said is probably not true. I'm seeing things in quadrants 2 and 3 that might cause us problems. My point is, this formula will never lie to you. That's what I was trying to get to. This one could lie, this one can't. Because of that, I just trained myself to go with sine over cosine sum and difference. More work, yes, but at least I'm guaranteed I'm not doing the question twice. There. That's what I was trying to say. We good? Okay. Okay. I will tell you, there is stuff like this on your test. Just like this, what we're looking at right here. I've given you cosine alpha is 1/3, but I've told you which quadrant you are in. That's quadrant -1 if you want to think of it that way. You see it's from 0 to negative pi over 2, which doubles as quadrant 4, right? This is quadrant -1 / quadrant 4. I'm telling you sine of beta is 1/4, but specifically you are in quadrant 1. Cool with that? my strongest suggestion ever is draw these pictures. Let's go ahead and draw them. So let's draw a triangle alpha in quadrant -1 / quadrant 4. The picture's not drawn to scale, of course. So alpha is here. There's alpha. X over R. And our beta is in quadrant 1. Mm, no, not a root 2. Here's beta, and sine is y over, oh crap, I did that in blue and it was supposed to be in red. Sorry guys, my apologies. There we go. I like my angles to be red. Anyway, we have a 1 here, we have a 4 here. So we are going to have to do the Pythagorean theorem here. 9 minus 1 is 8. So this is the square root of 8, which is 2 root 2. But it's negative because of where you are. This one's going to be the square root of 16 minus 1, or, squaring that. 16 minus 1, which is 15. So this is the square root of 15, and it is positive because of where it is. And there we go. All right. So the only time that the tangent sum or difference identity could really get you in trouble is when you're dealing with 45-degree angles only. The reason why is because in some quadrants, 45 degrees, sine and cosine have opposite symbols, which means the bottom could end up being undefined. But since I'm going to have a quadrant, an angle here that's not a 45 and an angle here that's not a 45, I know it's safe for me to use the tangent sum or difference identity. The 45, 45, 90 triangles are the only ones you have to be scared of. Or, of course, quadrantals. Okay. Otherwise, you're good to go on the regular old identity. Wait a second. That doesn't say an angle plus an angle yet. So you don't know what we call double angle identities. So how would you evaluate tangent of 2 theta using current knowledge? Come on. Yeah. No, I think it was Brooks, right? Or was it Kip? It was Brooks. He says that 2 alpha is alpha plus alpha. And that's exactly how you're going to handle this. We're going to call this tangent of alpha plus alpha. So our sum or difference formula for tangent is tan A tan B. Of course, they're both alpha, with a matching symbol on top. So tangent alpha plus tangent alpha over 1, opposite symbol, tan alpha, tan alpha. Oh, cool. All I need in order to evaluate this is to know what tangent of alpha is. Well, tangent of alpha is y over x, right? So we look to alpha, and we see y over x. Tangent alpha is just -2 root 2. So we just drop that in. Oh, you know what? Real quick, before I substitute, I'm gonna clean this up just a little bit because it hints at some of stuff that we're gonna learn tomorrow. Tangent alpha plus tangent alpha is 2 tangent alpha. And tangent alpha times tangent alpha is tangent squared alpha. Interesting. It's almost like we just derived a double angle formula for tangent. Cool. Well, anyway, we'll talk about it tomorrow. So 2, tangent alpha is right here, -2 root 2, over 1 minus Negative 2 root 2 quantity squared. Running kind of low in space here, aren't I? My math is going to have to get skinny. Sorry. Suck it in, mathematics. On the top, you're going to have negative 4 root 2. And on the bottom, the 1, the minus. Okay, let's see. You're going to be squaring the negative 2, which is 4, and squaring the root 2, which is 2. So it's 8. That gives me negative 4 root 2 over negative 7, which is 4 root 2 over 7. Neato mosquito. But if you want to talk to me about it, please, by all means, ask me any questions that you have. No? I just realized I forgot to stop my video, so I don't know if the audio is going to come out correctly in the video. Yeah?
I just have a question of how you determine what the tangent is equal to. Like, how do you know it's negative 2?
Tangent alpha?
Yeah.
Because tangent is y over x, correct? There's my y value, and there's my x value. Oh, I hope this whole video wasn't wrecked because I forgot to stop my video. Ugh. So many moving parts. Any other questions on it, or are we good to go? Ready to rock and roll? Okay. Well, let's figure out what sine of alpha and plus beta is. Grab a handy dandy pen. Actually, before I do, let's write the identity. The sine identity goes sine cos, cos sine, same symbol. Lots of s's in that statement. Sine cos, cos sine, same symbol. So I'm seeing the other things that we're going to need. We need to know what sine of alpha is, cosine of alpha, sine of beta, cosine of beta. So I'm going to come up here to alpha. Sine is y over r. So sine alpha is negative 2 root 2 over 3. And we were told cosine alpha, it's right there. It was given to us. It's 1/3. That's given information. Now if we go down to beta, we were given sine of beta. So we don't need to find it again. It's right there. But we do need to find cosine of beta. Cosine is x over r, which would be root 15 over 4. And we have all the things that we need in order to evaluate sine of alpha plus beta. Sine of alpha is here. Negative 2 root 2 over 3. Cosine of beta we found right here. Root 15 over 4. Cosine alpha, that was handed to us. It's right there. It's 1/3. And sine of beta, also handed to us right there, 1/4. Yep. All right, let's see what we get. Well, we know we're going to have a negative here. I have negative 2 root 30. 2 times 15 gives me root 30 over 12. And plus 1 over 12. Well, I can't reduce square root of 30. There's no perfect squares that I can divide 30 by. So your answer is legitimately just combine these two numbers. And this is in a weird order, so I'm going to write it in a different order. I'm going to write 1 minus 2 root 30 over 12. And there you have it. and then I'm ready to field some questions if we have them. Are there questions like this in the textbook, in the homework? I don't remember. We haven't gotten that far. McKinley, you said you did all but three of them. Were there things like this in the homework or no? And these are probably maybe the three that you didn't get to, or like that. Okay. All right. So now we have all the tools that we need in order to pull those off in the homeworks, correct? Oh no, we're doing it. I was just making. Hmm? Yeah, I wasn't gonna do this one, and then I thought, you know what? Why not? But I can tell you, I didn't have you do any tangent proofs on the test, tangent reduction proofs on the test or in the homework. And on to our last question. Wow. Yeah, I'm gonna go ahead and tell you, I left you a lot of space for a reason. It wasn't because I just had one more question and I couldn't fit it on the previous page. Oh no, no. It it's a pretty serious result. Okay, so don't write too large. Simplify sine of negative 5 pi over 12. And I'm thinking, I'm tired of writing in blue, so I'm going to switch over to purple. All right, well, I'm going to be honest with you. I want to deviate slightly from the way I have it in my notes, and the reason why is because I feel that these things are difficult to work with when they're in radians. Honestly, I think they're easier to do with degrees. So I would like to convert this negative 5 pi over 12 to degrees. So what we know, and what Max is remembering, is that a pi over 12 is equal to 15 degrees. Pi over 12 is 15 degrees, because pi over 6 is 30 degrees. This is half of that. Make sense? Since pi over 6 is 30, this is half of the pi over 6, so this is half of the 30 degrees. So this is actually asking you to find the sine of negative 75 degrees. That's 5 times 15. Sine of negative 75 degrees. All right. So 45 and 30 both negative. That is one of the many, many ways to do this question. So since McKinley mentioned that one first, let's do it that way. So what we're going to do is we're going to say that this is sine of negative 45 degrees, and then we'll say minus instead of plus negative, but minus 30 degrees. Which is absolutely not how I have it on my paper, and I don't care. It doesn't bother me one little bit. Heck, who knows? Maybe this will be an easier way of doing it. So we have the sine difference formula going on right here. The sine difference formula goes sine cos, cos sine, same symbol. Sine cos, cos sine, same symbol. Looking to me like I need to draw a negative 45-degree angle and a negative 30-degree angle. Well, negative angles, those open the wrong direction, don't they? So both of these angles are going to be in quadrant 4, aka quadrant negative 1. Picture's not drawn to scale, obviously. No, I'm adding a negative 30. Oh, I see what you're saying. I see what you're saying. Since I'm adding a negative, my apologies. Since we're thinking of it as like that, this needs to be a plus sign. The way I wrote mine. I'm sorry. Good catch. Was that Briar? Well, the only reason I ask is because I wasn't looking to my right. I'm trying to remember voices. Isabella, my video is not paused. Okay. Oh no, it's okay. It's probably just going to be a terrible recording. That's all. So yeah, I could have done this if I wanted to keep this a minus sign. Then both of these 30s we need to be positive 30s. But since I wrote in pin and that wasn't an easy fix for me, I could pretend that this said plus negative 30 and I could change that to a plus. So either way would have given us the exact same answer, to be honest with you. I just couldn't fix my boo-boo, so I had to change it to a plus negative 30 degrees. What do we have here? This is a 45-degree reference angle, and this will be a 30-degree reference angle. Bless you. Side lengths across from the 45 are 1s, so we have a 1, 1, root 2, but because of where we are, that needs to be a negative 1 on the y's. And across from the 30 is also a 1, but it needs to be a negative 1 because of where we are. Our triangles are filled out. We are ready to go. Just going to scooch up. There we go. Sine at this angle is going to be y over r, so negative 1 over root 2. Cosine at this angle is going to be x over r, or root 3 over 2. I use the negative 30, so I get to say plus. Cosine here, x over r, 1 over root 2. And lastly, sine here, which is going to be y over r, or negative 1 over 2.
You said that the one before it was negative and you didn't count this.
Which one's negative?
Uh, Never mind, no, it's not.
Okay. So multiplying straight across here gives me negative root 3
Wait.
over 2 root 2. Yeah, what's up, Max?
Yeah, cosine of negative 45 degrees is negative.
No, cosine's x over r.
Oh, okay. This makes
A sine would be y over r. Only one would be negative because we're in quadrant 4. If we were in quadrant 3, they'd both be negative. And then here we have negative 1 over 2 root 2. Well, hey, we have a common denominator, but my strong suggestion is that you rationalize your denominators before you combine these. It will make your life easier, trust me on this. And we rationalize denominators by multiplying the top and bottom by the no-no. And the no-no is that root 2 that's in the bottom. You don't want that. So let's multiply by a root 2 here and here for both fractions. It's going to give me a negative root 6 over 2 times, and root 2 times root 2 is 2. So 2 times 2, so 4. And a negative root 2 over 4. Giving us the grand result of
1.
oh no, you can't do subtraction here. You have to write it just negative 6 or negative root 6. I wrote 2. Whoops. Well, it doesn't matter. Order doesn't matter if we write it like this because they're both subtraction. Hey, my phone's not on mute. How about that? Sorry about that. Just mute my phone real quick. There we go. And we have our result. Negative 2 root 2 minus root 6, or negative root 6 minus root 2 all over 4. And the only thing you have to do is make sure that, actually no, we're solid. That's it. We're good. But what I did want to point out to you was the circular nature of how these notes are. The very first example in the notes was cosine of 15 degrees. Look at the answer. Cosine 15 degrees, sine of negative 5 pi over 12, or negative 75 degrees.
Is it always some variant of that?
Well, why would it be some variant?
Oh, because it's 15 degrees. Oh, no.
Well, 15 degrees and what was this angle?
75 degrees.
75 degrees. And what relationship do 15 degrees and 75 degrees have?
They're 60 degrees away from each other.
Well, that's not wrong, but um, right. But what relationship do the numbers 15 and 75 have in triangles? Come on, guys. It's academic vocabulary here. Starts with a C.
15 plus 75 equals 90.
Ah, they add up to 90. They're complementary angles. Remember, sine and cosine of complementary angles are equal to each other? The only reason why these weren't specifically equal is because this said negative. But if it said positive 5 pi over 12, we would have gotten the exact same answer that we got in the very first example. Because sine and cosine of complementary angles are equal. Neat, huh? Um, no, it's not easier. It's just completely different. Let me show you what I had on my notes. My version, I used a subtraction formula, and I didn't change it to degrees, but I think it would have been easier. But what I did was I said that it was 45 degrees minus 120 degrees, which is the exact same answer. So no, it's not. I mean, other than the fact that I didn't change it to degrees, but I think that degrees is a much easier thing to work with. I mean, that's just my opinion on this because I didn't have to try to find common denominators and stuff like that uh, up here in the fractions. But you see, we get the exact same result. And then I had what I was talking to you about. This was our first example, cosine of 15 degrees. I put that 75 up there to show you that sine of 75 degrees, which is 5 pi over 12, would have given you the exact same result. And what we did is we just reflected this triangle down to quadrant 4. We didn't reflect it, we rotated it down if you want to think of it like that. Put the 75 here, so we still have that root 6 plus root 2 across from a 75. It just happens to be negative because of where it is. So there will always be a root 6 plus root 2 across from a 75. You see, this is another special right triangle. I don't need you to memorize it, but it'll always happen like that. So at Max, you asked if there's always going to be some variant of it. Yes, there would be, because the 75, 15, 90 right triangle is a special right triangle, and the ratios are always going to stay the same. Pretty cool, huh? At least I think it is. I say it all the time. Mega nerd over here. But that's it. I think we're good to go.